Okay, so this question is all about the Drude model in free electron theory. And let's see, so first part is to describe the Drude model briefly. So basically, the Drude model is a conductivity theory that assumes that the electrons behave classically as just particles. Uh, there's no interactions with either with the ions or with each other. No Coulomb interactions, no potentials. And they only interact via collisions. So the electrons can collide with each other, they can collide with the ions. That's the only source of resistivity in the theory. So part B is to calculate the density of conduction electrons in aluminum. So we're given the density of aluminum, the atomic mass of aluminum, and the number of free electrons in every atom of aluminum. So to get the number density of electrons, I'm going to call it N. This is simply going to be the density, so 2.7 times 10 to the 3 kilograms. We're just minus 3. And that's divided by the mass. That's going to give us a number per meter cubed per volume. And this mass is converted to kilograms. Or let me write it in scientific notation. So this would be 2.7 times 10 to the, let's see, this is equal to 2.7 times 10 to the minus 3 kilograms. Or 2, sorry. And then that's going to be per, for one atom of aluminum. So then each atom is going to have 3. So it's going to give us how many atoms of aluminum there is. And then we have 3 electrons per aluminum. And this one's simple to calculate. It's just going to give us 3. So the 2.7s cancel. We just get to 10 to the 5th. So we get 3 electrons per meter cubed. Or, sorry, 3 times 10 to the 5th electrons. Not just 3. Per meter cubed. And then part C, to calculate the root mean square velocity. So root mean square velocity just means to calculate the energy that that you need to reach thermal equilibrium, basically, at some given temperature. So if we just say the kinetic energy of the electrons moving in this gas is given by this, 1/2 mv squared, and that has to be equal to just the thermal energy, which is 3/2 kBt, kB being the Boltzmann constant, and 3 coming from the degrees of freedom of the electron. So solving for this, it just gives us the halves cancel, and this gives the root mean square velocity. And I'll let you plug in the numbers for that, but it's just 3 times kBt, and T being 25 Celsius. And then mass of the electron. And you want to use Kelvin or Celsius. Sorry. Use standard units for everything. Now, it depends on what kind of kb, but you want to use joules for Kelvin here, so you're going to convert this to Kelvin. Part D, this is where you need to know your formulas for the Drude model. So Drude model, you can calculate that the resistivity is given by this. So it's the number density, the electron charge squared. This is the persistence length, or persistence time, so how long it takes for an electron to go without a collision, and then the mass of the electron. So plugging this in, n is going to be the n that we found before, meters minus 3. This is just the charge of the electron, E, should be 1.6 times 10 to the minus 19 coulombs squared. And we don't know the time. And then the mass of the electron. And then we know this has to be the resistivity of or the conductivity, sorry, 3.65 times 10 to the 7 ohms per meter per ohm meter. And then you can solve for this. I'll let you plug in the numbers, and you can solve for tau. And you just plug in. And D, so the Wiedemann-Franz law, it just says that the heat conductivity and the electrical conductivity divide to be some constant that depends on temperature. This constant being the Lorentz number. So how do we prove that? So we know the conductivity, electrical conductivity, is this one. And I'm going to assume you covered this, but the heat conductivity is simply 1/2, or 1/3, sorry, the volume heat capacity, the number density, some persistent length, and the velocity. So let's plug in. So kappa over sigma is going to be 1/3 heat capacity, number density, persistence length, and V. And then let's substitute for tau. It's going to be our velocity times divided by the persistence length. So if we plug in, then we have NE squared over ME. And then here we have the, this is meters per second. Meters, this is backwards. So it's length over velocity. So simplifying, the lengths cancel and the n's cancel. So we have 1/3 CV E squared over ME velocity squared. And if we plug in our velocity that we found before, we have, this is 1/3 CV E squared ME, and we found the RMS velocity here, so let's plug it in, and we have 3 kBt ME. So our 3's cancel, and you should have found, you probably know this, but CV, the heat capacity for metal, from the Dulong-Petit law, it's just 3 kb over m. So plugging in, we have in total is 3 kb squared E squared over me cubed. and that is our Lorentz constant times temperature. That's it.